What does it take to discover something? Perhaps you need a powerful telescope to look for distant planets, or a high energy and very expensive collider to look for new kinds of particles. But how far can you get with no tools? How far can you get with a mixture of mathematical intuition, a lot of perseverance, and a little bit of luck? This week's guest is the Hungarian mathematician Gábor Domokos. Gábor discovered an entirely new shape. And you might think, well, that's not that impressive. I can just draw a squiggle on a piece of paper and say, that's a new shape. And you might be right, that might be a shape that's never been seen before. But the shape that Gábor and his collaborators discovered, the Gomboc, has an unusual property. In fact, a property so unusual that many mathematicians thought that this shape simply couldn't exist, neither in nature or even in the abstract space of mathematics. For me, there are many fascinating aspects to this story. One is the shape itself, which we'll discuss. A shape that doesn't seem to exist naturally in nature, although now it's been manufactured. But then there's the quest to find it, which took over a decade. And in relating it, Gábor gives just beautiful anecdotes, but also one gets a feel for the frustration that he felt at times. But then there's a whole program of research which flourished from the discovery of this shape and from the kind of tools that it employed, particularly the way of categorizing shapes by the number of balance points that they have. And this is just something which, if you listen to this podcast, you'll learn how you can name or categorize the trillions of pebbles that you can find on a beach. And not only that, how you can pick up a pebble in your hand and feel its age just by feeling for the number of balance points it has. And this is something universal, something geometric. So this has been applied to understanding rivers on Mars and the pebbles there, and also understanding putative alien spacecraft, which turn out to be more likely to be a comet, not to mention turtles. So there's a few loose threads right there. Listen on, and I promise these will get tied up. I'm James Robinson, and this is Multiverses. Gábor Domokos, welcome to Multiverses. Thanks for joining me.
Thank you for having me. It's a pleasure.
So there's many interesting strands to your research, but it seems that there's a kind of central idea that they've flown from, which is this notion of a shape which many thought was impossible. So many mathematicians thought that there was a shape a three-dimensional shape that had properties that just couldn't hang together. You couldn't have this shape, not only in nature, but it just didn't work as a concept. And so there were mathematicians who were trying to prove as a theorem that this shape couldn't exist. But then the story turned out quite differently. So perhaps you could tell us a bit about what that shape is, what the properties were, and that made it seem that this thing couldn't exist. That's very abstract. Hopefully you can make it a bit more concrete.
Well, the properties of the shape are rather simply described. If this shape, the name of the shape is the Gömböc, and if you put such a shape on a table, then it will always get back to the same stable position like a weevil. And the other equally important, or maybe even more important property is that it only has one unstable balance point. So one stable to which it returns and one unstable from which it runs, so to say. The stable point is very easily visible in an experiment. The single unstable point is much harder to see, but it can be seen. But that is not a tabletop experiment. Now, this shape, it is the ultimate shape because we know that a smaller number, so this has two balance points, as I said, a stable and unstable, and a smaller number cannot exist. That is a fact. And in the plane, so in 2 dimensions, it was known that the minimal number is 4. It is always an even number. And the minimal number in the plane is 4. And this fact, so if you take a planar disk and let it, a homogeneous disk, and let it roll along its perimeter, then like an ellipse, then it would always come to rest at 2 places at least. And between these 2 places, there will be other 2 which are the unstable points, like the ends of the long axis. Now, this was known, and the 3D version, and this is connected to another theorem, which is called the 4-vertex theorem, which says that a planar smooth curve has at least 4 extrema of its curvature. So this seemed like a well-established mathematical fact, and people were looking for a generalization in 3D. And one possible generalization was that also in 3D, the minimal number of balance points would be 4. And this was a big temptation. So as you said, people tried to prove it. It looked like a beautiful theorem. And there was no counterexample known. So nobody has ever seen an object which had less than 4. And well, when you are kind of fumbling around, then this mathematics is not just about the proof. It is about intuition. And there was a strong intuition that for the past few thousand years, nobody has seen anything like this. It looked like a fundamental thing. And if nobody has seen it, that probably doesn't exist. So people were putting their bets on the non-existence mostly.
We should say here
I
as
can
well,
say,
I was just going to say, I think one thing people might be wondering as well, what about the Weeble, which you mentioned very early? But the reason that has...
the Weeble has this property, as you point out. Yes, it has the property of having just 2 balance points, but it has another property. It has an added weight, which is sitting at the bottom. So if you are admitted to put in weights, then it is very easy to do this. And until now, I forgot to mention, I think I mentioned once that we are talking about homogeneous objects. So the material is completely uniform. And then everything is controlled just by the shape. So the geometry is translated directly into mechanics. There is no additional information. And so people were trying to prove this, and with confidence I can say the people who were trying to prove this were very much more versed in mathematics than I am, probably brighter than I am. But in mathematics, no matter how bright you are, if you are trying to prove something which is not true, then you are bound to fail. And the story took a turn when in 1995, Vladimir Arnold, who was at that point one of the most celebrated mathematicians, and with good reason, he just offered the conjecture that there could be a counterexample. Now, if anyone else would have offered this conjecture, it would not have been taken seriously. But since he was the man who had the best chance to prove anything about this problem, this was a very, very strong fact. And I was the person who got lucky, and he just told me this conjecture. So that was kind of a personal luck.
there
And
was
in this
it was
case,
more than there
I
was an
think this was what turned the tide.
Yeah, I was going to say I've heard you tell this story, and there's an element of luck, but there's also some persistence on your side to try to talk to Arnold, who was, as you say, just this mathematical superstar at the time. And I think you had to.
Yeah, he was.
Uh, is it right? You had to sort of you kind of had to pay to access him, as it were, at the conference.
Yeah, yes, indeed, indeed. So it was in Germany. It was still before the euro, so they had the German mark, and I was a young postdoc or something like that, and I got like 60 German marks from the Germans as a stipend to come for 1 week to a conference to which I only went to see Arnold live. And he was one of my main heroes at that point. So I saw that he's, as a young man, I saw that he's a kind of scientist whom I really admired, because he was not just a mathematician, he was a much broader kind of thinking person. He told that mathematics is part of physics where experiments are cheap. And that was his approach to science. So I really wanted to see him. And when I got there, I went to his talk, which was given to a huge crowd. And nobody understood the talk, but everybody understood there was a recurrent theme that some quantity was bigger or equal than 4. And the number 4 was something everybody could understand. But then I realized that this might be the same number 4 I have been thinking about. So I was with my friend Andy Ruina and Jim Papadopoulos. We proved the case, the 2D case, earlier. And then we started to think about the 3D, but we just couldn't get a hold on that problem. And I thought that this might be related. So this number 4 could be the same number 4, because Arnold was talking about many subjects. But then I could not access him because everybody wanted to talk to him. And as I said, the Germans advertised that if you pay 30 marks, which was 50% of my budget, you can be seated with a celebrity of your choice at lunch. And that was this lunch, which I still remember, where I paid the money. I went on a diet, a very slim diet for the rest of the week. And, and I was seated at the same table, but as due to the efficiency of the Germans, there were 15 other people. And every single person wanted to show something to Arnold, so he couldn't eat. And then he just asked at the end of the lunch, "What is your result, young man?" And I told him there is no result. It was so awkward that I wanted to get out. And then finally I got lucky and I still could talk to him. And then he knew I came from Hungary because of my badge. And he knew I paid the 30 marks. So he knew I had to have a very good reason to go to that lunch. And so he basically insisted that I tell him what it was about. I told him, and then it turned out I did not understand much of this problem. In this conversation was a little bit awakening for me, because it turned out that I did not understand the problem well. And he told me that probably there could be a shape out there, and then he left. And if anybody else would have told me in any other circumstances, I wouldn't have paid so much attention. But then I thought that this could be really interesting. And I was digging in for 10 years. And I found many properties of this shape which I didn't know whether it existed, but I realized that if it existed, it is really a miraculous shape. And then I was again lucky because I got a brilliant grad student, Peter Varkonyi, and then the problem started to converge on a really a nice math problem. Originally, it was more like a philosophical problem, whether it existed or not, and how to put. It was very hard to have grabbed this problem because there is no algorithmic approach to find such shapes, even today. With computer, you cannot do it. And I was even searching among Pebbles to find this shape, and I couldn't. So it was a desperate thing. And in these 10 years, there were ups and downs. And in the downs, sometimes I started to doubt whether Arnold was right. Sometimes he was wrong. Most of the time, he was right. But then we could come up first with a theoretical construction, proving that it existed, but that construction could not be manufactured. And then another year later, we could produce something which could be manufactured. And the first copy, which we gave the number 1, we brought to his birthday to Moscow. And that was a very interesting event. So in many ways, and we gave it to him, and we got a lot of feedback. And part of the it was in his style. The feedback was definitely in his style. So
Okay.
he was so basically he told us it was a good job, but now we should start to do something serious. So that was the main message. But otherwise, he immediately pointed out that this finding is a mathematical thing, but its significance is probably not in pure math. It's probably in natural sciences. That was his basic intuition, and immediately he told us to look for pebbles and to shapes. And at that point, I did not understand again what he was talking about. It took me again a couple of years, and unfortunately, he died in 2010. So he couldn't see the second wave of ideas coming from his intuition, getting into being realized. But that proved to be probably more fruitful than, I mean, it reached many more people because the Gomboc is rather popular in many ways, but it was not clear at the beginning where this would lead us. And his suggestion that so the number 2 is somehow hardwired into this shape, and it is a philosophic not it's not a philosophical problem, it's a more physiological problem, how we think about shapes, because the brain is divided into left and right, and the part of the brain which has the linguistic skills and the numbers and so on is different from the part which has this kind of geometric intuition. And this, as a result of this, we cannot speak about shapes. We have no words for shapes. When mankind is conquering anything, like an island, the first thing is to give it a name. And or we discover anything, then we give it a name. But if you look at the shapes, there are very few of them have names. We have trillions of shapes around us, literally trillions of shapes. And we have, if I ask anyone, how many names can you give? You can give a dozen names. And that is a big, big handicap, because if you cannot talk about something, that is, uh, even in real life, if you are not admitted to talk about something, or you are unable to talk about something, it is very hard to think about it. And then, despite landing on Mars and all that kind of achievements and having the iPhones, we are still severely handicapped by talking about shapes. And this idea is not changing this, but a little bit, because this gives a way to assign numbers to shapes. Once you get numbers, it is like a name. So numbers and words are basically the same. And you can assign names in many ways. You can assign names in an arbitrary way. You go to the beach and give a name to each pebble, but that is meaningless. We would like to have names which are encoded by nature. So we want to discover what is the name of that shape. We don't want to give it a name. And we have to acknowledge that there are many more shapes than we have names. But still, if we can give a meaningful name to a collection of shapes, that is already a big step forward from where we are now. We have names for some idealized shapes, which I would call degenerate, like the sphere or the cube. Physically, you cannot have a sphere, because if you have an error by an atom, it's not a sphere anymore. You cannot have an exact cube. They are ideal shapes, like Platonic kind of ideas. For real shapes, we have no names. And And this gives you a chance, this kind of idea, this started an avalanche, because it turned out that you can give it a number. The Gomboc has the number 2, and then you can talk about other shapes having other numbers. And actually, it has 2 numbers, 1 and 1. So we have a table. And then it turns out in each field of this table, say 2, 2, which is the ellipsoid, you can do subdivisions, and you can go in and you can do a catalog which is more detailed, and then you can dig in even more and you can do an even more detailed catalog. This catalog will be never as fine as many shapes you have. It will always give you categories, but because these categories are defined by nature, so we are not inventing these numbers. We are taking a pebble, taking an asteroid, taking whatever shape you give me, and we determine these numbers which have been inscribed by nature. Therefore, this is a natural catalog. And these numbers are telling. They tell us where this shape came from, how it evolved, because the evolution of shapes is imprinted in these numbers. These numbers evolve with the shape. And there are very simple rules. So one very simple rule is that, for example, in an abrasion process, the general tendency is to get rid of these balance points. So this number is getting reduced, no matter how you do it. If you do it on a large scale, the statistics is it starts from somewhere, which I will explain later, and then it gets reduced. So they move, in some sense, they move towards this Gomboc shape, which has the minimal number, but they never get there. Yeah. So this gives you a kind of a good view, a bird's eye view from a very complicated process, which is universal in space and time. It has been going on for billions of years. So it's a useful thing. So Arnold sparked this whole thing. He was the mastermind, and yes, we were the lucky guys at the right time at the right place, and we tried to make the best of it.
Well, I think you understate the persistence. We can touch in on some.
Yeah, we were persistent, lucky
You were
guys.
persistent. I think it's been told to me, everyone has luck, but it's really how many times you roll the dice, right? That's what separates success from failure.
I acknowledge that. Yes, you need to have persistence. Yes, I take credit for believing Arnold for an extended period of time, and then yes, and there was a piece of luck.
Yeah.
Yes.
I want to. So I want to read back some of the things you just said, because I think this is really, like you say, this is perhaps the bigger idea. Many people will be familiar with the Gomboc or the Gombocs because it is such a fascinating shape. It's a wonderful desk toy, the way it sort of rolls in such an unusual way, right? Like unlike anything else in nature. But the bigger idea is, how do you talk about shapes? And as you mentioned, whereof we cannot speak, thereof we must remain silent, right? If we don't have a way of talking about pebbles or other natural shapes, we can't think about them. And this idea of classifying them by the number of stable and unstable equilibria, which you say gives you this kind of infinite chessboard, if you like, with at the origin the Gombocs at 1-1, and then from that you have shapes with 1 stable, 2 unstable, or 2 stable, 1 unstable, and in fact there's a way of showing that as long as you have the Gombocs, all those other shapes are possible, because there is a way of changing, knocking a corner off or what have you, or knocking a bit of curvature off to create every other shape from that. So, but it is an immensely, I think I want to ensure that every listener, when they finish hearing this, is able to go to the beach and actually have a new way of thinking about pebbles. At least we should say the convex pebbles, so the ones that don't have any sort of inward curves. which are, and probably about half of pebbles are convex. And all you need to do is pick up a pebble, and you can see you can quite easily find the stable balance points by just
Yes.
finding where it rests down, and just looking at a pebble. You'll have a very good intuition of where those balance points are, which way you need to turn it to find a balance point. And then to find the unstable ones, if one thinks of sort of an ellipsoid pebble, where, like you were saying, it's got sort of this long edge, this sort of it's rather long and thin, as it were. Often you can see again, but if you can't see, you kind of pick it up in your hands and you put it on. You support it so it doesn't wobble in one plane, and let it within another plane kind of find its stable point. Is that a good procedure? Have I? Or maybe that's better for saddle points, which are another form of equilibrium. But probably this is easier if people actually try it.
Yeah. So if you want to do this with a hand experiment, then it is very easy to find the stable ones. And if the pebble is sufficiently flat, then it is very easy to find the unstable ones either also, because you stabilize it in the plane of this flatness where it is very flat, and you roll it around, and in that roll you will feel there are stable points constrained to that plane and unstable points in that plane. Now the points which are stable in that plane but otherwise they are not stable, they are the saddles, and which are still unstable even constrained to the plane, they are the two unstable points. So this is not a complicated experiment, and some geologists are already doing it. On the other hand, of course, for a complicated shape, this doesn't work. And I mentioned that there are finer subdivisions, not just the number of these points, but also their arrangement can be found. These are identified by graphs. There are several types of graphs which tell you how these shapes are arranged on the surface of the pebble. And those are really not for hand experiments, but now we have computer programs which, if we have a scanned pebble in 3D, then we can tell these numbers. So but it is fun to go to the beach and have a look. Now you also
I think it is for maybe 100 pebbles, but I know you spent a whole holiday with your wife looking at. I think.
we spent a holiday with my wife. I still didn't know whether there was a Gomboc, and this is a mathematical problem seemingly.
Yeah.
But if you go to the beach and you find a good shape, then you solve the problem, assuming the shape is homogeneous. But most pebbles are, well, and then you can reconstruct it and check it. But you have a good chance to solve the problem by finding a suitable pebble. But I didn't find, and then we did 2,000 pebbles. But since we have done many more pebbles with my students,
Hmm.
and it is really, you are gaining a lot of intuition,
Yeah.
and it is not just about the mathematics. You learn.
Yeah.
So we spent days and weeks and months. Um, there, I can tell you stories. So, but not just here in Budapest. A student of mine went to Southwest Australia to measure the pebbles. Another two of them went to New Zealand, and then somebody went to Puerto Rico. So
Hmm.
we participated in expeditions, basically, with geologists to get a feel on this,
I
because
think that.
it is not just about the mathematics. You want to be sure that the data you are talking about is robust, and that is not, you cannot get any kind of intuition about this without wading into the rivers and creeks and picking up the pebbles and measuring them and comparing the numbers. So now, after some years, we have a pretty good understanding, and we feel that this is robust data.
Yeah, I think that there is a really important point here that actually we often find that things are sort of discovered in mathematics and then find some application within physics later, and someone comes up with some, I don't know, imaginary numbers or something, and like, oh, actually this turns out to be really useful in, I don't know, quantum mechanics and all over the place. But there's almost an element of this story which is the reverse. Even though you didn't find the Gombocs on that beach with your wife, who we have to give a lot of credit to as well here for accompanying you in this
She
quest.
did not file. She didn't file a divorce. Well, some people might have done this. I mean, we went for a holiday, and I suggested as a social program that each evening we pick up, say, 40 kilograms of pebbles at the beach, bring to the hotel, and then classify them based on the Poincaré-Hopf theorem. This is the Poincaré-Hopf theorem, which gives you the numbers, relationship between these numbers.
Mm-hmm.
So some marriages. So this is a bifurcation point for any marriage because it can go two ways.
But yeah, so yeah. By the way, the Poincaré-Hopf theorem, I guess that relates. I mean, many people will think of that about in terms of hairy spheres and not being able to comb a sphere, but actually it also shows that there is a relationship between stable, unstable, and number of saddle points.
Yes.
So what, which sort of means if you know you can have this plane categorized in any two of those three variables, and then you can
Yes.
derive the third one. But the point, yeah, I think one thing I've heard you mention is that when you went presented the first Gomboc to Arnold and showed him the work that you'd done on it, you were surprised to see that he was so interested in what you'd done at the beach, because for you that had seemed like a kind of fruitless
Yeah.
endeavor. But I think there was maybe a slide where you showed sort of kind of like almost like a set of boxes which represents
Yes.
that plane, a part of that plane. So you had a box for 1 1 empty because you didn't find a Gombox, but then you had a box for one stable or two unstable and two stable equilibria, and that was sort of filled with pebbles. Like there was a lot in that box, even that which is weird because it's right close, it's so close to the Gomboc box, and then sort of to the right and below that box, as it were. So if you think about going to three stable equilibria and three unstable equilibria, moving away from that point, you had boxes with fewer pebbles. And here's some. Arnold saw that as kind of empirical data, I guess, but he
Yeah.
also recognized in it perhaps that there was an echo of some kind of fundamental process going on here.
He immediately saw it, which I didn't see. So I showed this slide as to illustrate a fun story and to illustrate a major failure. So I saw that we failed. And after the talk, I met him in the elevator, I think, or somewhere. And after the talk, he made a comment about the pebbles, which I didn't understand. And then after the next day, I met him in the elevator and he said, "Did you understand my comment?" And I said, "Sorry, I didn't." And then he said, "But I enjoyed your talk. And do you know which was your best slide?" And I was guessing and guessing and guessing. And then I guessed this one with the pebbles. And he says, "Yes." And I said, it was fun. I said, he said, "No, that was not fun. That was a Markov process." And so he immediately saw two layers behind this, and he was right again. These pebbles are migrating in this table based on a very strict rule, which is a stochastic process, but stochastic processes are very well defined things, and they are migrating in this table, and this process are bringing them randomly. So there is some randomness. It is like Brownian motion. Brownian motion with a drift. Brownian motion would not bring them anywhere. They would just wander around. but Brownian motion with a drift. It brings them into this corner, but almost never does it bring them beyond the boundary of 1 and 1. They don't get there. And we know why. But the whole process is strictly controlled by this motion. And what Arnold saw, what his eye saw, my eye saw it only 3 years later, that if you apply this process to anything, then you get a very well-defined distribution in the end, which we call a stationary distribution. So you put down million pebbles and you play this game and you wait a million years. And then you will have a stationary distribution of pebbles in these boxes. And he saw that what we measured was very, very close to that distribution. I of course, I did not. But then, after some thinking and some learning, because then he told us, now you have to learn mathematics. Of course, I didn't know how did such a Markov process really work. So I had to learn. But after learning, after doing computations, we saw that yes, this is the governing process. And again, well, I wish I could have shown you some later results, shown him some later results as well, because these led to some interesting discoveries. So it is not just, it's a good feeling to give names. As you pointed out, it makes you more comfortable. But nowadays, people in science asking for results. Philosophical advantage is not counted as a result. Uh, but we could translate this into some tangible results, which the scientific community recognizes as results. So we were working with some NASA people to unlock the history of pebbles, which have been photographed by Curiosity on Mars. And based on their current shape, we could backtrack the pebbles, and that we could tell, based on the current picture, we could tell how big the pebble originally was. Now, if you tell that to a geologist, he becomes a happy person, or she, and tells you how long the river was. So this sounds like an outlandish question, but they know they know the gravity, they know the kind of rock, they know everything, they know the slope. If you tell this pebble was originally this big, they tell you how long the river was. And that was the question NASA was actually looking at. So that is something which you can sell on the scientific market. You cannot sell this kind of philosophical jazz that you give names to shapes and then this is a cognitive advantage. And so this is not something you can actually market as a scientific result. For me, this is very important. But then you have to convert it into things which society feels it's useful. And we had moderate success with we had some such achievements, mostly in planetary science. This was one example. Another case was this asteroid, this Oumuamua. It came in, and this is the first intergalactic object ever tracked and observed by humanity. And the first thing they noticed, it is either very flat or very thin. That was for sure because of the reflection of light. And almost immediately, Avi Loeb, who is a very famous astrophysicist at the Harvard Smithsonian, he concluded that this is probably a spaceship. And
Because it
even
looks
though,
like a pencil, right?
yeah,
What's
it
you know,
looks either like a pencil or a disc. We don't know
right?
which of those, but either a pencil or a disc.
And
And
that's an
you
odd shape.
don't see these shapes
Yeah.
in space normally. And every single radio telescope on Earth was directed onto this thing, and they were trying to find the little green guys running around and giving the signals. And there was no signal. I don't know. I mean, I was not there. There is no evidence supporting or either in favor or against this claim. So there is no scientific conclusion. However, our theory told us that if you take any shape and you let it travel for 500 million years straight line in the intergalactic space, then probability one, it will be either very flat or very thin. So this is Occam's razor. So it's a very simple explanation, which does not mean that it is true, but it has some appeal compared to the spaceship. And I have no firm standing here. I cannot claim that it was not a spaceship. I just claim that there exists an alternative explanation which is very simple and appealing, and it is connected to a conversation, because if you have something which is very flat, it's bound to have exactly two stable points. And if you have something which is very thin, it's bound to have exactly two unstable points. So we are in the second row or in the second column of the table. And as I just explained, this migration of pebbles in this table ends up in the second row and in the second column. So this is some ultimate shape. So what we just saw is something which has undergone abrasion for a very long time, and in the solar system we cannot see these guys, because if you get very thin or you get very flat and you undergo a slightly bigger collision, then you break.
Right.
And while the solar system appears to be kind of empty, it's not empty compared to intergalactic space. Intergalactic space is much, 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 much emptier than the solar system. So the chances of getting to these ultimate geometries, which are very thin or very flat, are way higher if you are traveling out there. So in the solar system, if you are just going around in the solar system, the probability is very slim that anything could evolve to this kind of very matured state. But in the intergalactic space, yes, it is a reasonable thing. And we think that was one explanation. And again, returning back, so a philosophical theory about giving numbers and names turned into something which catch the interest of very good astrophysicists. People have been reading this kind of note, and we got some feedback. So I think it became something which you can call useful, right?
Yeah.
Explaining nature to some extent or giving an idea about nature, whatever.
I mean, I think it's fascinating that you can look at the shape of rocks on a beach or the shape of rocks on Mars and say something about the history of those rocks and how, how what their original size was, how much they've been abraded. And I think we should make this, we should probably just clarify, yeah, how this, the mechanisms at work here, because we said everything sort of wants to move towards that 2-2 square.
Yeah.
And it is, it's not particularly fancy. It's abrasion.
Yeah.
So just things rubbing against each
Simple.
other. It's simple in a kind of more or less random way.
Yeah.
I wanted to add as well. I guess the exact form of the process of abrasion determines whether you end up with these sort of ellipsoid type shapes in that 2-2 box, or these
Yeah.
long thin sort of. I'm gonna say this wrongly. Oumuamua shapes.
Oumuamua.
Yeah. Okay. Oumuamua. Say that one more time.
Oumuamua.
Okay. You're well practiced at saying that. And it's as you say, the long thin, the sort of pencil type shapes and long and discs are quite susceptible to being broken. So if you think about pebbles, they're fairly large, and so if it's pebbles abrading amongst each other, you tend to not to get those shapes because a collision can fracture sort of a long thin thing. Whereas if it's wind abrasion, then you do get these, and you can kind of imagine that you see this in deserts where I suppose you see these quite long or quite sharp pieces of rock.
Yeah.
Is that a kind of right, more or less correct explanation?
Yes, this is very good. I did not talk about this yet. So it's a size dependent thing. And the curious, so if something is being aberrated by objects which are much larger than itself, then the shape would become rounder. If it is being aberrated by things which are much smaller than the shape, then it will become more angular, more elongated. What sounds like a miracle, though, so these are totally opposite evolutions. What sounds like a miracle, though, that the number of balance points appears to be decreasing in both cases. Although the way the shapes evolve doesn't even resemble each other. So in one case, things become like more like spherical, and in the other case, become like you can get a tetrahedron, or you can get a flat disk, or you can get like thin shapes, and still, so if you there is a number called the isoperimetric ratio or the isoperimetric quotient, which measures the sphericity of an object. And if something is being aberrated by large objects, then this isoperimetric ratio is going up. Its maximum is 1, and that is the perfect sphere. And if it is being aberrated by small objects, like as you mentioned in the desert, a rock is being aberrated by sand, or you are an asteroid in outer space and you are being aberrated by meteorites, then the isoperimetric ratio is going down. So it is completely opposite. But in both cases, the number of balance points is going down. So this is really, and that makes it the more interesting. So and if you are on a beach and you are a newcomer to a beach, you are a big rock being thrown onto a beach, then initially you are being aberrated by things which are much smaller than you are. Then you become smaller. You become a peer to them because you are about the same size, and then you become smaller than your neighbors. So this whole thing makes a big U-turn. And anything which is related to classical geological understanding of shapes, like the isoperimetric ratio is more or less classical geology, is non-monotonic. So it either so even if it is monotonic, it could go up or it could go down, but in many cases it is not even monotonic. It goes up and down in the life of one single pebble. And if you have anything which is non-monotonic, or it is monotonic but you don't know the direction of monotonicity, then from the current value of that function, you have no way to deduce its past. But if a function is monotonic, then in mathematics we say it is invertible. That means that from the current state, so you can basically backtrack things if you have a monotonic evolution. And we have no full mathematical proof for this, for the monotonicity, because it is not a deterministic monotonicity, it is a statistical monotonicity. For special cases, you can prove deterministic, and we have good understanding where the source of randomness is coming from. But if you look at data, data tells you that this is an overwhelming thing. It is going on. So if you measure these numbers, they are just going down. And one way to think about this is that if you look at a shape, you explained very well that if you take something in your hand, immediately you see, unless it has many. So it has many points, you don't see it, and a common way to say it is a complicated shape. And if you have few points, then it is, you would tend to say, in a common phrase would be a simple shape. So this whole aberration process is simplifying, and it taking out what was the original character of that shape. It is redressing the shape with new features which are simple features. And therefore, because this kind of simplicity, achieving simplicity, is an overbearing principle, when you catch a shape and you see how simple it is, you can tell how mature it is. It tells you on what stage it is in this evolution. And Oumuamua happened to be a very matured, a very simple shape. It is not a coincidence that in a podcast, we are in a podcast, but we can talk about the shape of Oumuamua because it had such a simple shape. It
Right.
was either like a disc or like a pen. If it had been like a very complex shape, we could not talk about it.
Right. Yeah, and that, as you say, it is striking that these very different, they're shapes that we can talk about, but discs and ellipsoids look to us very different, or pencils, discs, and ellipsoids, and yet they all fall within this same 2-2 box. And yeah, it seems that was a revelation to geologists, geomorphologists, who before would have, were using this isoperimetric ratio and other things to classify shapes, and would have given very different classifications to the various shapes falling within that box. But as soon as you apply this other lens, this other language of talking about things, you actually see that they're all following the same process when talked about in the language of equilibrium points. So yeah, that is really striking. The other thing I wanted to mention was, yeah, this idea of shapes becoming more simple. And I was curious if you've ever thought about this in terms of kind of entropic terms, and how each box seems to be like a kind of macro state. So, one of the ways of thinking about entropy is obviously you have how many different sort of micro states fit within a particular macro state. And if you have lots of different ways of making something that sort of, in that coarse grained way of talking about things, is the same. So the classic example is lots of different ways you can arrange something to have the same, volume and temperature and so on. Then that is a high entropy thing. And if it's very hard to make that macro state, that high level object, like if there's only one way you can arrange things, then it's very low entropy. So I suppose we could say in some ways the sphere seems very low entropy because there's only one way you can arrange stuff. There's only one thing in that box, if we even think of it as being something you can put on this plane. And the Gomboc as well seems to be quite low entropy. Although, as you say, there's no kind of computer way of generating all the different Gombocs.
Yeah.
Is that something that can be categorized? I don't have a strong intuition on this.
Yes. So one can. I mentioned earlier that there are these boxes which you mentioned, and inside each box there are small boxes.
Mm-hmm.
So subcategories.
So they're like the microstates, and the
They
large
are the
box is the kind of
microstates,
macrostate. Yeah.
and but it is somehow, the further you go from the Gomboc, the more microstates you see.
Uh-huh. Yes.
And that is a fact. So that we know. And in fact, it is exponential. So if you go out in 2-2, you just have two microstates. And then as you go out and increase the numbers, and you get more and more microstates. I don't want to say bad numbers, but I kind of remember one number. So if we say that s plus u equals 9, so we are on a diagonal, right? Then I think altogether we have over 70,000 microstates already. And that, so in this sense, it's and yes, if you converge to the corner, this number of microstates is dropping radically. Next to the Gomboc, in 2-1 and 1-2, there are only one microstate, which I would call a microstate. And these states, these microstates, they are characterized by graphs, very simple graphs, by the way. And the way when things get aberrated, these graphs are also evolving. And the way they evolve by things which mathematicians love. They evolve by phase contraction. So there is a graph and it loses its faces
Right. Okay.
as it converges. So yes, one can think of this in this manner.
Right.
And there is another manner in which you can bring in entropy. If we just look at the aberration where you are being hit by large objects, then the shape is evolving towards the sphere. And what happens is it is like the heat equation, but in a geometric way. In the heat equation, you have an object and you insert heat sources, and then you let it dissipate. And then heat, after some while, it converges to uniform heat state. Now, the same is going on here, but heat is a conserved quantity. So the total amount of heat in the object remains constant, but it becomes more and more uniform. So it is an entropy thing. Now here, curvature is replacing heat. The Gaussian curvature of any object which is simply connected is constant. It is 4 pi. And if you look at a polyhedron, then it has no Gaussian curvature anywhere except at the vertices. So this would correspond to an object where you have point heat sources. And the equation, what it does, it is smearing out curvature. And when curvature is uniform, this corresponds to the uniform heat. It is a sphere. So yes, people have written, it is called curvature entropy. And for some special case, curvature entropy would evolve also in a monotonic manner. And people have written about this. So this is probably along the lines which you suggested. So this is one way to think about entropy. And the other thing is about graphs. But in both cases, we come back to the concept of simplicity or complexity. Yes. And it is uniform. It is
Yeah.
uniform, at least in the statistical sense.
In some ways, it's striking though that things evolve to a lower entropy state. That's sort of the opposite of a physicist's intuition. But of course, there's probably other ways of describing the entropy here. It's a kind of slippery,
Yeah, well, it is a
and we would
slippery thing. You can look at it like this or this, but I think what we should notice, there is an entropy concept and there is a monotonicity.
yes,
Now,
yeah,
whether you look for entropy or negative entropy,
right,
then this is just a binary question. We have an entropy concept and we have a monotonicity. So your
yeah,
question was spot on. Yes.
yeah. There's one. I wanted to make sure that people. I do. The heat equation is really interesting here, but and so maybe we can come back to that. But I wanted to make sure that everyone has a. There's one model which you've given for this process, which I really like, is I think whether you're a mathematician or just someone who uses soap, you're going to know this model. And it's in terms of, I mean, I think you know the one I'm referring to. So I'll let you talk about it in terms of a kind of a cubic or a rectangular bar of soap.
Mm-hmm. Yeah. So if you take a rectangular soap bar, which is like a cube, then and you wash your hands, which you should do, then you will notice that the shape of the bar will change. And it will not change in a self-similar manner. So it will not remain a rectangular shape. It will become rounded. And as in this process, as we just mentioned, things change. The volume changes, the mass changes, the angularity changes, but there is one thing which stays constant, and that is the integral of the Gaussian curvature on the whole surface. So that remains constant, and that means that initially all this curvature was concentrated at the vertices, at the sharp vertices, and it was absolutely non-uniform. In mathematical language, we call this Dirac deltas, where are the vertices for curvature. All the curvature was there in 8 Dirac deltas. And then afterwards, it gets smeared out. And if you are doing it very carefully, the hand washing, you are lucky, you get to a kind of a spherical thingy. Now, this is very interesting analogy, and it is not just a folklore thing, it's more than that. You can actually write down these equations, so you get something which is very similar to the heat equation. And just to tell you a curiosity, we were talking about the Mars rover curiosity, but now I tell you some different curiosity. In the heat equation, one can prove that if you insert a heat source, the heat will change in the whole object instantaneously. And this is not physical. So heat is propagating faster than light in this model. And this is, of course, an artifact because this is a linear partial differential equation. And linear models tend to have kind of funny aspects. Now, the curvature dissipation model we are talking about, the abrasion model, is a highly nonlinear equation which can be linearized. But it's very difficult stuff. I don't know much about this. So this is very technical, hardcore geometric PD stuff. There are a handful of people on the planet who work on this. Now, one of them is Richard Hamilton. He's very famous. He's a great mathematician, and he got credit, partial credit, for the solution of the Poincaré conjecture. So Gregory Perelman came up with a solution, but the solution was based on something which Hamilton has invented, which was called the Ricci flow. And Perelman refused the money and the prize and everything. Hamilton got some credit, very well deserved credit. So he's one of the great geometers and PD people now. Believe or not, when he invented the Ricci flow, they were in 4 dimensions, of course. They were out there. But to flex muscle, they did some experiments or they did some kind of exercises in lower dimensions, in 2D and in 3D. And Richard Hamilton himself wrote a paper about the shape of worn stones. And this is, needless to say, it's a sheerly brilliant paper. But it tells you something which is really interesting. If you are diligent enough to dig into that paper, it is not a bedtime reading, but it is something exceptional. So Richard Hamilton tells you that while the heat equation has this property of infinite propagation speed, the curvature flow does not have it. It has a finite propagation speed. And back to the soap, if you do it carefully, buy your soap, start to wash your hands, and you will notice that after finite time, maybe small time, the middle part of the flat sides will be still completely flat. So curvature does not propagate immediately to the total surface. It takes a little bit of time. And that was a revelation for physicists because now it resolved this puzzle. What does the heat equation, why does the heat equation tell us of infinite propagation speed? This was the answer. Because it's linear. And this is the nonlinear equation. And now we have a finite propagation speed. I think this is a beautiful, this small bit, a beautiful how mathematics is contributing to physical understandings. And it is about the soap analogy, which you mentioned. Anybody can test it.
Yeah. And I think it is. I mean, I don't understand enough about the Poincaré conjecture to know if this is a good intuition or not, but it does seem like there is, a reason why. There's an interesting analogy, at least, between the Poincaré conjecture and Pebbles, right?
Oh, yeah,
Well, the
yeah.
Poincaré conjecture is in a higher dimensional space, as you say. It's essentially saying, and this was an unproven conjecture until Perelman, using some maths from Hamilton, proved it a few years ago. So
10 years ago, more than
10 years ago. Okay. So it'd gone 100 years unproved after
Yes.
Poincaré had said, okay, if I get this right, every kind of surface in a four-dimensional space where you can take any loop and collapse it onto a point. If you have that property, you can morph that surface into a three sphere, so a sphere in that four-dimensional space.
So, in fact, the Poincaré conjecture, in general sense, was living in several dimensions. So it was
Okay, even
just, and
not just the three.
we don't, maybe we don't, I am not an expert on that, but what I can tell you that it was proven in steps. And in each dimension, the person who proved it got the Fields Medal.
Right. Okay.
Yeah, one of these people was Stephen Smale. And it went on and on and on. And Perelman was the last. So it was the most difficult part.
Right.
And
Okay.
then he finally nailed it. And to do that, he needed a tool. And basically, Hamilton invented the tool. And the tool was a horribly complicated geometric partial differential equation. That was the tool, the hammer, which Perelman needed. And that equation, if you write it down in three dimensions, it is the governing equation for the abrasion for Pebbles. It is not something analogous. It is the equation.
Yeah. And
So
that makes sense, right? Because you're morphing. The whole proof is to try to morph something onto a sphere, and that's exactly what's happening. With the pebbles, they're trying to get to.
Exactly. So it is exactly the equation in the case when the pebble is being hit by large abrasives. Then the Ricci flow restricted to three dimensions, which is a Gauss curvature flow. This is a Gauss curvature flow. So we have an object, and each point is moving along the surface normal inward with a speed proportional to the Gaussian curvature of that point. So that is a Gauss curvature flow. Now that is the governing equation for abrasion by large abrasions. This was found. So the general case, it was not clear how this fitted into this huge picture until Hamilton and Perelman came about. But people were trying to do this. I mean, the first person to write down this equation was Fiery, and then it was generalized to different kinds of apparatus. But the big picture, the geometric picture, became apparent when these guys started to work on the Poincaré conjecture, because then they started to prove miraculous theorems about the curvature flow in two dimensions. And then they didn't do much in 3D. One exception is this paper of Hamilton, when there is a hand-drawn sketch of an abraded pebble. And Hamilton writes, I wish somebody would do this on the computer or in a lab, because then I could see it. We often tend to say that mathematicians are just out there, but this is not always quite true. So sometimes they have a good intuition about the physics as well.
Yeah, and it's I guess I was really I loved that quote from Arnold that maths is a part of physics where experiments are cheap. I'd never heard that before, but it sort of runs in reverse as well. Clearly maths can learn something from physics, and I know you've put a lot of pebbles in drums.
Yes. It goes both ways. Yes.
Yeah. And I mean, the heat equation.
If you have these people, I mean, if you look at these people, Arnold, maybe Hamilton, I don't know Hamilton, but in case of Arnold, I have talked to him 3 times. And I know that his mind was racing back and forth between physics and maths. And he picked the bits from here and brought it over there and going back and forth. If you go to an average mathematician, he expects you to bring a problem which can be solved by the part of mathematics he knows. That is a natural thing. If you go to somebody like Arnold, you bring a problem and he creates the mathematics on the fly to solve the problem. So it is a very different view. And as you pointed out, mathematics can learn from physics and the other way around. That is a very healthy
Yeah.
kind of dialogue.
I know you're fond of the quote from Galileo, which, by the way, Julian Barber, who was a guest on this, loves this quote as well. That uh, the language of nature is mathematics, and its symbols are, I think, is it triangles and circles, and
Yes.
uh, and then the final piece of that quote, which is just really seals the deal, is like, and if you don't have those, you're in a darkened labyrinth. You're not just in a labyrinth, but someone's turned out the lights, so you're really lost. But again, there's those two aspects. Like that quote has the two ideas in it. The one being that you can learn about mathematics by reading off nature, right? You can uncover the symbols of that book by looking at nature. But then, of course, you can play it the other way and you can do pure mathematics and discover some symbols that you then go out and find in nature. But
Yeah.
it's so curious that the Gomboc, for instance, is something that doesn't seem to. It's one of those things where it was inspired by nature, but actually doesn't exist in nature.
Yeah, that is nicely put. That is nicely put. So let me make a few comments. So, yes, I do like this quote, and it goes back to an earlier part of our conversation because Galileo says a lot in this quote because he not only says that nature is written in the language of mathematics, the book of nature, but he specifically says that it is about shapes. And as we started off in this conversation, we discussed that we don't know. I mean, we have a very limited understanding of these shapes, and that may be a global handicap. I mean, if this is true, if this hypothesis is true, and nature is constructed in a language which relies on shapes, then we have a very limited ability to understand it. There are many directions in which you can see this that geometric objects pop up at, at string theory or where so geometric objects or Plato's theory of the elements, uh, which could be discarded as like a myth, but as you know, Heisenberg and or contemporary Frank Wilczek, they were both kind of advertising this theory, saying that it has some vision because it says that matter is matter ultimately matter consists of objects which have symmetries and which are identical. So at the core of the things again we see a geometric idea. I don't claim that everything is geometry, but what I feel is that geometric ideas pop up in a very broad range of subjects. And what I definitely know that our ability to grasp geometric objects is limited, and this might be a reason why part of mathematicians prefer algebra.
Yeah, yeah. It's interesting. I think possibly Julian Barber might claim that everything is geometry, which I think he probably would. We're sort of running low on time, but there's one just on this idea of how do you classify. Nature seems very, very detailed and hard for us to give names to, and so yeah, we just have these these platonic shapes. We've discussed one of the ways that you can talk about shapes, but I know that you've worked. There's another idea I want to introduce of yours, which is around counting sort of faces and the number of faces per for each vertex. Yeah, could you kind of outline that, even if we don't have time to go into all of the
Yeah.
details of it? I think it's just such a nice idea, and that will give listeners one more tool in their box.
Mhm. It's a simple idea. So you go to any park or your yard, front yard, backyard, and you grab a handful of crushed rock, which can be seen all over the place. And you notice that these shapes are angular shapes. They are not smooth. They have edges and vertices, They look like polyhedra. They're not quite polyhedra, but they're kind of polyhedral. And then you kind of approximately count these numbers, the number of faces, the edges and vertices. And if you do this again persistently, we have done it persistently, and you take a big average, then you find that the average number of faces is 6, the average number of vertices is 8, and the average number of edges is 12, which is exactly the numbers of the cube. And this was the element Earth in Plato's theory. So he said Earth is consisting of cubes. But what we found is that this is true in a Platonic sense. Plato was always looking behind things, and he said that there is this analogy of the cave where the prisoners see the shadows, but they cannot see the real object. So, in the Platonic sense, these shapes, these crushed rocks, are just distorted images. And if you look at with the naked eye, you just see many different shapes. But if you look with the eye of your mind, you take the average, you see the ideal shape, which is a cube. And this is a pretty universal thing. There are exceptions. There are processes which produce fragments which don't abide by this rule. But on Earth and in other planets, in many cases, this is what we see. So you have to be able to fit them together. And the way they fit together, on average, they give you these cubic averages. Now, again, we have a multitude of shapes, zillions of shapes, but we can make some relatively simple statement. Whether or not Plato knew this, it is way beyond my pay grade. So I don't know whether he knew it. But let us look at it like this. If you go to a psychologist, she or he will tell you that your mind is averaging out every 5 seconds something. So this is a very standard thing what we are doing. We are looking around and we are averaging. It is beyond doubt that Plato's mind was probably slightly better than the average mind. I think this is a safe thing to say. Now he was walking these beaches, he was looking at these things. Is it possible that his averaging brought him some intuition? I don't know. But it is certainly tempting to believe that maybe this theory has some quantitative, and even it was not, he didn't know this, he certainly helped us to find this simple fact. It's a very simple fact, but it helps to, again, to talk about numbers. So the cube has 6 stable, 8 unstable, and 12 saddle points, so 26 balance points. If you look at crushed rock, on a broad average, it would have 20 odd balance points. Not as much as the cube, but almost in the same range. And if you go to the beach, you find that most pebbles have 6, like the ellipsoid. So nature on Earth, on other planets, now and for the past few billion years, everything was happening between the numbers 20 odd and 6. That was the process. Things were climbing down from the numbers. So this is the start of the process. Nothing has more than that. So we start at that and in that range at 20. So the cube and the Gomboc are standing like two brackets, which we don't see actually in this process. We don't see perfect cubes unless you look at crystals. But in crushed rock, you don't see the perfect cube, and you don't see the Gomboc either. But these are the outermost things. And although we don't know individually the fate of every shape, for the mind, it gives a little bit of support to know that this whole process, which is a very, very broad thing, it is happening within these limits, within these brackets. And then this helps to maybe to talk about it
Yeah,
or to
I think this
understand.
is it certainly does, and I'm reminded of something that Harvey Brown, a philosopher of physics, once said about the film 2001. He said, "What's so strange about that obelisk?" And it's because it's like a perfect obelisk, right? It's got
Mhm.
these perfectly flat Platonic sides, if you like. And so that's, it's an elongated cube, right? It's one end of the bracket, and that's why it just doesn't look natural. And I do wonder if Kubrick was to remake, come back from the dead and make a new 2001, would it have
Yeah,
a
yeah,
Gomboc in
yeah.
it, right?
I looked at this movie, of course, not just once, several times, and yes, this occurred to me that the fact that a cubic object was featured there, uh, maybe it was not a coincidence. So the cube has a central role in our thinking, and this has several reasons, and this might be one of the reasons that it is in front of our eyes in nature in a kind of a non immediate or not non obvious way, but it is on display.
Hmm.
And this is so in some sense it's an ultimate shape. It's more ultimate than other shapes. So maybe Stanley Kubrick had this intuition, or maybe he was reading Plato. I don't know, but I certainly like the movie.
Yeah. And yeah, it's just so it's immediately recognizable that this is something that's alien, right? This couldn't have been produced by nature.
Yes,
Yeah, so it's
yes, but
because
it
it's one of
is
those
not.
brackets.
It could have been icosahedron, but it being a cube is being something which is
Just
just outside,
yeah,
just
yeah,
outside nature.
yeah.
And again, we can argue whether Plato knew or whether Kubrick knew, or they were just having this intuition. So I don't think it matters actually. It just matters. So the mind is working in a very complicated way. And Poincaré, of whom we talked today, he was not just a great mathematician, he was also a very good writer. He wrote some he was eloquent writer. And he wrote some good books. And in one of his books, he's talking about how the mind is working. And his understanding is that the geniuses are not basically different from the smart people by being having more brain power or something like that, but they have a better kind of channel of communication with the subconscious. And and he thinks that in the subconscious, the large amount of thinking is done, and some people get these pops. And this there is evidence because many people have experienced that while going to sleep or waking up, you get a flash. And that is where your subconscious is still there and it is communicating with the conscious mind. And Poincaré is telling us stories about from his life, and it was obvious that it's some sudden flash. And he says it is not a heavenly insight; it is just from the subconscious. And we tend to know that brilliant people tend to be sometimes a little bit unstable. And if it is true what Poincaré thinks, and the subconscious is freely communicating with the conscious mind, and then it is not a miracle that they are a little bit less less stable. So we don't know about Kubrick, we don't know about Plato, but we know that both of them were attracted to the cube, and they were not the only ones. Picasso was also attracted to the cube,
Yeah,
and yeah,
yeah,
and Marcel Breuer was also attracted to the cube. So there were some people attracted to the cube, and maybe there is something to it.
yeah. We dream of these impossible things, or almost possible, but beyond what we see. So yeah, I think that's a good place to that's a good point to conclude on. We need to dream more.
Yes, yes, dreaming is a good thing. And thank you for your questions. I mean, you wrote in some cases more than I did. In particular, thanks for bringing in this movie. I I have been thinking about this, but I not now. It was in my subconscious, but you brought it in, and I think this is a very good touch. I mean, some people can connect to this much better than to partial differential equations.
Yeah, well, I think that may be many people. But yeah, thank you so much. It's been a real pleasure.
Thank you, James.